For those of us with a particular fascination for robots, we need a special understanding of the robot heart. The unromantic among you, no doubt, call the robot heart a battery. Inside a battery, chemical reactions occur which involve a transfer of electrons. Reduction, or a gain of electrons, occurs at the cathode. Oxidation, or a loss of electrons, occurs at the anode. Reduction, oxidation, redox is the name given to these battery reactions. Since an electrochemical cell of this type can be designed using a wide variety of materials, we can personally build a heart for our robot. But before we get heartistic, let's consider a few basic principles. If we take a chunk of zinc metal and drop it into a solution of copper sulfate, wait a few minutes, and the zinc becomes covered with a brown substance. Also, we note that the blue color of the solution fades. Let's imagine that we have bionic eyes so we can see what is going on inside the solution. The atoms of zinc are surrounded by water molecules, as well as copper ions and sulfate ions. The interaction occurs between the copper ion and the zinc atom. So let's focus on these two. Copper holds on to its electrons more strongly than zinc. So a copper ion attracts electrons away from a zinc atom, which becomes a colorless zinc ion and floats off into solution. As a result of the electron transfer, the copper ion has become an atom of metallic copper. As the zinc atoms change to ions, the zinc metal gradually disappears. It is replaced by the copper atoms that are created, producing a brown deposit. The removal of the blue copper ions causes the color to disappear from the solution. In the interaction between the copper and the zinc, the copper ion acts like a bully, which attacks the zinc atom, seizing 2 of its electrons. There are other ions, like mercury, for example, which can take electrons away from the copper atom. And there are atoms such as magnesium, which will give up electrons to zinc ions. It's as if there is a pecking order among ions, allowing chemists to list them in order so that those which are more easily reduced are placed on top, and those which are increasingly difficult to reduce are placed on the bottom. This list is called the activity series and includes many other elements. But for now, let's concern ourselves with 2 of them, zinc and copper, and see how this difference in the tendency to become reduced can be used to construct an electrochemical cell. We've already seen how the copper ion and the zinc react. Once again, a zinc atom loses electrons to a copper ion. Now, if these 2 elements can be separated, but still made to react, then a flow of charge will take place between them. With the right equipment, we can harness a flow of charge. Time now to get artistic and build our robot an electrochemical cell using zinc and copper. First, we must keep the zinc and copper apart by creating separate half cells. In one, we put a metallic zinc electrode immersed in a solution of zinc sulfate, which will dissociate to form aqueous zinc and sulfate ions. In the other, we place an electrode of metallic copper and a solution of copper sulfate containing copper and sulfate ions. Let's connect them with a wire so that the electrons can flow from one electrode to the other electrode. But nothing happens. That's because our circuit is incomplete. We have a highway for charge to flow in one direction, but not in the other. To provide the link, we will use a salt bridge, which contains ions such as potassium and nitrate. Let's see if we can figure out why this works. We know that zinc is more easily oxidized than copper. Perhaps zinc acts as an anode, with zinc atoms giving up 2 electrons per atom. The resulting zinc ions would enter the solution, and the electrons released from the zinc could flow through the connecting wire to the copper electrode. Since copper ions are reduced more readily than zinc ions, the copper electrode could act as the cathode, where copper ions are reduced, gaining electrons. This would cause them to form copper atoms, which would stick or plate out onto the electrode. If we watch a cell as it works, sure enough, the zinc electrode gets smaller as the zinc atoms become ions and drift into solution. On the other hand, the copper electrode becomes larger as copper atoms plate out on it. The flow of charge seems to be what we've predicted. So, why the salt bridge? Because without it, there can be no current flow. Why? Well, in the anode half of the cell, there would be a buildup of positive charges. And in the cathode half of the cell, positive ions are removed, so there is a buildup of negative sulfate ions. This buildup of opposite charges is called polarization, and it quickly causes the electron flow to stop. It is the salt bridge that prevents a buildup of positive charge. In the zinc half of the cell, it allows the positive ions to migrate to the opposite cell. In the copper half of the cell, negative ions can migrate to the opposite side. Together, these migrations prevent polarization from occurring. This process gives the impression that negative charges are being attracted to the negative terminal and positive charges to the positive terminal. Of course, it's the flow of electrons that makes an electrochemical cell useful. The flow of ions is also essential to an electrochemical cell to complete the circuit. But wait now. Before you install this piece of heartwork in your robot, are you sure it'll do the job? After all, there are so many different redox reactions to choose from. However, you don't really need to build by trial and error. In the electrochemical cells. And that's the subject of our next chapter. All right. Life isn't always a bed of roses, even with a robot. No arguments, perhaps. But sooner or later, the honeymoon is over. And there are all those little service problems that you'll have to cope with. Yep, weak batteries again. Are we stuck with the same old off-the-shelf batteries, or can we possibly build a better battery? In the earlier chapters, we considered some battery basics. Now let's learn how to design a supercell so that your robot can help you realize some of your wildest fantasies. We've seen that an electrochemical cell can be thought of as 2 half cells, in which the electrodes consist of different materials. At the anode, oxidation occurs. In this particular cell, zinc atoms lose electrons to become zinc ions. As electrons flow from the anode over to the cathode, their energy can be harnessed. At the cathode, reduction occurs. In this case, copper ions are reduced to metallic copper. A salt bridge connecting the two cells allows for ion movement from one half cell to the other. The secret to designing a more energetic cell lies not in a different process, but in the materials used. But how do we know which combination will give our robot that little something extra? The best measure of the output is the potential difference it produces. Potential difference is measured in volts. And it's a measure of the energy that each electron can deliver as it flows from the anode to the cathode. We know that chemists list metals in an order which indicates how readily they gain and lose electrons. Now, if we choose two metals in the series for our cell, how might we predict their potential difference? It's a bit like trying to measure the height of two children located in different parts of a room. One approach would be to select one child and assign it a value of 0. Other children could be compared to that child. A positive number would indicate how much taller a child was compared to the standard. A negative number would indicate a child smaller than the standard. At a glance, we could compare the height of any two children. Chemists use a similar procedure. As an electrochemical standard, they have selected a hydrogen half cell. The hydrogen gas at a pressure of 1 atmosphere is introduced into a tube. The tube is immersed in a standard concentration of hydrogen ions, 1 kilomole per cubic meter. The electrode is made of platinum because it is chemically inert and doesn't interfere with the reaction. At the electrode, hydrogen ions unite with electrons to form molecules of hydrogen. The tendency for an element to be reduced in this way is called its half-cell potential, represented like this. A half-cell potential of 0 volts is assigned to hydrogen, the standard. Remember that no reaction occurs in this half cell unless there is another half cell. Take, for example, one in which a copper electrode is immersed in a solution containing a standard concentration of copper ions. A voltmeter connected to this cell will read 0.34 volts. Electrons flow from the hydrogen to the copper half cell, which means the copper ions have a greater attraction for electrons than hydrogen ions. We measure the greater attraction of this half-cell reaction occurring in the copper half cell by comparing this voltage to the hydrogen standard. Simple to do because the standard is 0. The half-cell potential of the copper reaction is 0.34 volts, greater than the standard hydrogen. The gain of electrons makes this a reduction reaction. Since the complete reaction is a redox reaction, over in the other half cell, the hydrogen reaction must be an oxidation reaction. Hydrogen atoms must lose electrons to form hydrogen ions. But the equation we originally wrote, in which hydrogen ions gain electrons to produce hydrogen, is a reduction reaction. Since the reverse reaction is actually taking place, we must reverse the equation. The two half-cell equations then correctly describe the reaction occurring in the cell. But as we choose different electrodes, things do not always work out the same way. Suppose we replace the copper half cell with a zinc electrode immersed in a solution containing a standard concentration of zinc ions. When a voltmeter is connected, it shows this reading. The needle swings to the left, which indicates that the electrons flow from the zinc half cell to the hydrogen half cell. This means that reduction is occurring in the hydrogen half cell. Hydrogen ions are gaining electrons and forming hydrogen atoms. In the zinc half cell, atoms are being oxidized to produce ions. Here's the oxidation equation and the half cell potential. Because chemists like to standardize, and since all reactions are reversible, they prefer to show half cell reactions as reduction reactions. Reversing the equation, we must also reverse the sign of the half cell potential. By comparing the hydrogen standard with many different substances, chemists have produced a table of reduction reactions and their half cell potentials. With this table, we can examine any two possible reactions, such as this familiar pair. Obviously, since batteries are all redox reactions, both of these reactions cannot be reduction reactions as shown. But which will it be? The higher half cell potential of copper compared to the zinc means that the copper ions will have a greater attraction for electrons than zinc ions. So the copper reaction will be a reduction reaction. And the zinc reaction must be reversed to become oxidation. And the sign of its half cell potential must be reversed as well. It's easy to find the potential difference for the reaction by adding the two half cell potentials. By using a list of half cell potentials, we can compare any two half cells without actually having to construct the battery. With this background, you can set about designing a super duper cell for your extra special cellmate. Now there's a robot who's got heart. And that's just what we've been after. A robot heart with the power to leap to our every command. With all this energy, naturally, the battery we're using is our own high-powered design. Well, not quite. In fact, we're using commercial batteries, which don't look at all like electrochemical cells we've been building. The problem is that our laboratory models aren't much use for commercial applications. They're too large and bulky for our robots, and they spill easily. But they are useful for establishing basic principles. They've helped chemists develop half-cell tables. When two half cells are selected, they can be quickly arranged as a reduction reaction and an oxidation reaction. Their half-cell potentials add together to give us a prediction of the battery strength. Although our laboratory models look completely different from commercial cells, they both work on the same chemical principles. In 1786, Luigi Galvani accidentally discovered these chemical principles. During an experiment, he hung a freshly dissected frog's leg from a copper hook. Galvani noticed that it twitched whenever it touched a different metal, such as iron. He found that when the leg was in contact with copper, nothing happened. Another scientist, Alessandro Volta, applying this idea of different metals, invented a primitive pile, or battery. Volta's pile consisted of silver and zinc discs, separated by cardboard, soaked in salt water. Like other early cells, this primitive pile could not deliver a flow of charge over an extended period of time. A French scientist, Georges Leclanché, is credited with inventing the cell which is still widely used today. The Leclanché cell has the same important parts as our laboratory model. The anode of the laboratory model is made of zinc and is actually the container in which the chemicals are placed. The wire connected to the cathode is replaced by a carbon rod. So, where's the cathode? It's a paste, a mix of manganese 4 oxide and carbon powder located in the space around the carbon rod. The rest of the space in the container is filled with a black paste containing ammonium chloride. But we'll show it in another color to distinguish it from the black cathode. We know that in our laboratory model, a salt bridge is required. It allows ions to migrate from one half cell to the other, and at the same time, the bridge keeps the two solutions from coming into physical contact. In the Leclanché cell, a paper liner soaked in a conductive material is used to separate the anode from the cathode. The paste inside the cell is moist enough for the movement of ions. The soaked paper liner allows ions to move through it, but it keeps the anode from making direct contact with the electrolyte that surrounds the cathode. Because the cell is full of paste, our robot will be able to assume a variety of useful positions without spilling his heart to anyone. Exactly how does the Leclanché cell produce the flow of charge that makes it so useful? It's not as simple as in our laboratory model, where the reactions are well known. In fact, in some commercial cells, chemists aren't sure what the reactions are. For the Leclanché cell, they're thought to be as follows. Remember, the anode is made up of zinc atoms. They react with some of the ammonia molecules dissolved in the electrolyte. The zinc atom becomes reduced by losing 2 electrons. The resulting zinc ion combines with 4 ammonia molecules to form a zinc-ammonia complex ion. To prevent a buildup of positive charge, negatively charged chloride ions migrate towards the anode, passing through the paper liner as they do so. At the cathode, it is the manganese 4 oxide that reacts. Some ammonium ions are also involved. 2 molecules of manganese 4 oxide, 2 ammonium ions, and 2 electrons react to form manganese 3 oxide, ammonia, and water. In this reaction, positive ions are being removed. As a result, ammonium ions migrate through the paper liner and towards the cathode. So, whenever the cell is used, there is chemical activity near the cathode and around the anode, as well as the movement of ions. The amount of current a battery can deliver is obviously limited by the amount of anode that can be changed from atom to ion and take part in a reaction. Wouldn't it be nice if the anode could somehow be rebuilt and reused? Well, technology has produced the rechargeable battery. One such cell is the nickel-cadmium cell. It has a cadmium anode and a cathode in which some nickel-3 hydroxide is embedded. The two electrodes are surrounded by a potassium hydroxide electrolyte. To supply electrical energy, the cadmium reaction loses electrons. The cadmium is eaten away, while the nickel reaction gains electrons. When this cell runs down, it can be connected to a battery charger and recharged. The battery charger forces the electrons to flow through the circuit in the other direction. The cadmium reaction gains electrons, rebuilding the cadmium anode. But unfortunately, rechargeable batteries are expensive. Unless a battery is rechargeable, the anode continuously erodes until it's possible that the container can be perforated, allowing the corrosive contents to leak out. So, absorbent cardboard is often placed around the zinc, and the entire battery enclosed in a steel jacket. No matter which variety of battery you might use, the cardboard and steel may not hold back the contents forever. Remember, if your robot runs down, he needs a change of heart, or he may turn into a nasty drip. Tiny batteries all over the robot's iron skin. Each drop of water which falls on the robot acts like an electrochemical cell. With an anode and a cathode. A pathway for electrons to flow and a salt bridge. That's the droplet itself, where migrating ions form unsightly iron oxides. If electrochemistry is the problem, it's also the solution. We can galvanize our robot by dipping him in a bath of zinc, which loses electrons more easily than iron. It's the zinc that oxidizes to leave a protective coating of zinc oxide. Safe, but very dull. A little flashier protection comes from robot jewelry, a sacrificial anode of magnesium. This forces the iron under a droplet of water to become a cathode. Magnesium donates the electrons, and the iron passes them on to the drop of water without losing electrons itself. Of all the ways of protecting your robot, the flashiest of all turns the robot into an electrode, connected to another electrode in what looks like an electrochemical cell. But there's a big difference. In a battery, we have chemical change, producing electrical energy. A horrible form of cannibalism. But if we change the process by putting a battery in the circuit and reversing the current, electrical energy now produces a chemical change. We can clothe our robot in a gleaming coat of chromium. This process is known as electroplating. We'll explore the process using a more familiar metal. We'll start with water and add copper sulfate. Most of the copper sulfate is in the form of positively charged copper ions and negatively charged sulfate ions. A very small number of water molecules will dissociate to form positively charged hydrogen ions and negatively charged hydroxyl ions. The remaining water molecules, although neutral, have regions which are slightly negative and regions which are slightly positive. That's because oxygen has a stronger attraction for electrons than hydrogen. We'll begin the electroplating process with a pair of carbon rods for electrodes. Of course, nothing happens. By now we know that they have to be connected for a charge to flow. But we won't stop there. We'll insert a battery in the circuit. Now we've got action. Copper atoms begin to plate out on one electrode. At the other electrode, bubbles are forming. What's happening? Let's explore the electrochemistry. The negative terminal of the battery pushes negative charges on one electrode. This electrode repels negatively charged hydroxyl and sulfate ions. It attracts the positively charged copper and hydrogen ions. It also causes water molecules in its vicinity to orient themselves so that the positive parts are nearer the electrode. You might think that positive ions and water molecules could all be reduced by accepting electrons from the electrode. But that's not what happens. It's as if copper ions intimidate the other particles and grab all the electrons for themselves. We can explain this by examining the half-cell reactions involved. Hydrogen ions, in fact, are not in a standard concentration, but scattered throughout the water. And so the reaction has a very low half-cell potential. And so does this reaction, compared to the copper reaction. Consequently, the copper ions grab the electrons and are reduced. As they do so, they plate out on the electrode. This reaction, the reverse of a battery reaction, is called electrolysis. The atoms of metal which plate out on one electrode gives industry its major use for electrolysis, the process known as electroplating. Since reduction is occurring here, the negative electrode acts as a cathode during electrolysis. Now, let's look at the positive electrode, which acts as the anode. The positive charge repels the hydrogen and copper ions, but it attracts the hydroxyl and sulfate ions. Water molecules nearby orient themselves so that the slightly negative oxygen is closest to the electrode. Let's look at the possible reactions and their potentials. Now, these are reduction potentials, but we are considering the oxidation side of the reactions. So we must reverse these reactions and change the signs of the potentials. This reaction has the most negative potential, so it won't occur. The remaining two reactions have the same potential. Let's explore the water reaction. Two water molecules lose electrons to the anode and form a molecule of oxygen gas and 4 hydrogen ions. It's the oxygen molecules that we see bubbling up at the anode. While the hydrogen ions tend to remain in solution, migrating towards the cathode with the other positive ions, the negative ions migrate towards the anode. This migration of ions keeps the overall charge of the solution neutral. By combining the reaction at the anode with the reaction at the cathode, we can determine the overall reaction, as well as the overall potential. It's a negative potential. This means that the reaction won't occur spontaneously. And that brings us to the reason for the battery. We need an electrical potential higher than 0.48 volts to overcome the negative potential of the process. In place of the carbon cathode, put a robot, and we can have a copper-coated robot. or, with different ingredients, a chrome-plated one. Electrochemistry, the curse of every Iron Man, causes rust. But electrochemistry is also the cure. So, if you're planning life with a robot, take heart. Better still, take a pack of 4. You'll need them to keep alive that special electrochemical romance with a robot.
Different values for the Greek letter epsilon produce the 4 conic sections.
Remember the good old days when your robot was young and romantic? Remember how his heart beat with fire? That special electrochemistry that gave him the power to perform your every dream? Well, dreams fade. A careless adventure or two, and before you know it, unsightly rust. Why does rust develop so quickly? Fortunately, we've been studying all those little services your robot will need. And we've explored the principles of electrochemistry within the heart of the robot, the battery. Fortunate because those same principles will help us to understand rust, which is nothing more than tiny electrochemical cells forming over the skin of our Iron Man. Let's consider a single salty tear of happiness falling on the head of our romantic robot. We'll look at the droplet in cross-section as it rests on the iron. The drop is surrounded by air. Air contains oxygen. Because of the drop, the concentration of oxygen next to the iron surface will be low in the center of the drop and higher at the edge of the drop. The edge behaves like a half cell, at which reduction occurs. Here, oxygen combines with water and electrons to form hydroxyl ions. But where do the electrons come from? The center of the drop acts as the other half cell, at which oxidation occurs. The iron in the center of the drop acts as an anode. Here, iron atoms become oxidized as they lose electrons to become ferrous ions in the salt solution. The electrons flow through the iron to the edges of the drop, where they are required in the reduction reaction. This matches the electron flow through the wire of an electrochemical cell. Now remember that an electrochemical cell requires the salt bridge. Without it, the cell very quickly becomes polarized and the flow of charge stops. The movement of the ions in the salt bridge prevents polarization from occurring and enables the cell to keep operating. The droplet of salt solution on the iron acts as the salt bridge. The negative ions, or anions, move from the edge of the drop to the center. This would include the hydroxyl ions and the chloride ions. The positive ions, or cations, move from the center of the drop to the edge. This involves the migration of ferrous ions and sodium ions. When ferrous ions moving in one direction encounter hydroxyl ions moving in the other, an insoluble solid, ferrous hydroxide, is produced. This substance is immediately oxidized to produce a hydrate of ferric oxide, the material commonly known as rust. This rust concentrates between the half cells, which are formed between the center and the very edge of the drop. From above, we can see that the rust concentrates in a ring between the center and the edge of the drop. So we can see that each droplet of salt solution that falls on the robot produces a tiny electrochemical cell. We can write half-cell reactions for rusting, just as we did earlier for electrochemical cells. At the anode, iron is oxidized to form ferrous ions. At the cathode, oxygen is reduced in the formation of hydroxyl ions. The two half-cell reactions add together to describe the overall reaction. You may wonder why ordinary raindrops also cause rusting. Well, raindrops contain dissolved materials, such as carbon dioxide and sulfur dioxide. These substances readily react with water to form ions. The result is very much like that of salt water. So, just what can we do to protect our iron treasure from embarrassing skin conditions or worse? We have time to consider several possibilities. We could make our robots of metals, such as gold or platinum, which are not readily oxidized. But can we afford it? Another possibility is to galvanize an everyday iron robot. Galvanizing means a bath in molten zinc. Zinc protects the iron for a simple reason. A look at the reduction table shows why. Since we are considering oxidation reactions, reverse the equations and reverse the signs on the potentials. Then we can compare oxidation potentials. Zinc's potential to oxidize is higher than that of iron. And that's what happens. Oxygen reacts with the zinc to form zinc oxide. Even if the zinc is scratched and the iron is exposed, the zinc on either side of the scratch is more likely to be oxidized, protecting the iron. As the zinc atoms combine with oxygen to form zinc oxide, they form a layer which protects both the zinc and the iron. Unfortunately, that turns yesterday's shiny, bright star into today's gray servant, protected but dull. Another version of this kind of protection is a little more flashy. Robot jewelry. Let's rivet on a bracelet of magnesium. Now, look at the reduction potentials of iron and magnesium. Reverse their reduction potentials, and we see that magnesium has the higher oxidation potential. When a drop of salt water lands on the robot, magnesium becomes the anode where oxidation occurs. The electrons released from the magnesium travel to the iron cathode, where they are passed into the drop. Since the iron is turned into a cathode, this is called cathodic protection. And the magnesium is called a sacrificial anode, since it reacts and erodes away. So, in the end, electrochemistry can be both a nuisance and a useful tool for keeping a romantic robot in at least serviceable condition. Now, the best is yet to come. In the next program, we will explore how the normal electrochemical reactions of a battery can be reversed to create a robot that's really flashy.